Hey everyone, this video is me working through chapter one of Richard Hammack's Book of Proof. It's mostly just getting me used to working on camera and recording myself and streaming, so I go through the material pretty quickly, but I hope it helps anyone out there working on the same material and enjoy. I'm probably just going to skim this because we already know what sets are. I just don't need to read every single thing in this book. All right, got sets. The sets have elements. Should be obvious enough for anyone who's taken a proofs class. Wow, two sets are equal if they contain exactly the same elements. Beautiful. Beautiful. The listing doesn't matter, of course, because that's just how we're representing the sets. You can represent the set of all integers in many different ways. This guy doesn't like 0 in his natural numbers. That's pretty common. Most people do not include 0, but some weirdos do. And when they do, you're like, hey, dude, what are you doing? Get that 0 out of there. Look at that. R, the set of all real numbers. Everyone has worked with it. No one really understands it. That must have been really annoying to write out. We're gonna have to write out some matrices eventually, I'm sure. I could go back and do linear algebra. It wasn't my favorite class, but it becomes very useful. It seems like it pops up literally everywhere. Set builder notation. Yeah, that's pretty useful stuff. Okay. I mean, I guess I should like. There's nothing I need to new information that I need to write down, but I'll write something down. All right, we have notes. Look at that. Look at that. We're taking notes. We can write as many notes as we want. We don't have a limit here. Some awesome sets. Set. No way that I can write it in here, but integers z average numbers is q. Real numbers is r. Look at that. The infinitely long line. Q is the set of all numbers in R. They can be expressed as a fraction of two integers, of course. Look at that. We're at the exercises. Look at how easy this will be. Okay, write each of the following sets by listing their elements between braces. All right, so if x is in Z, 5x minus 1. Okay, so it's increments of 5. So it's all increment. It's every multiple of 5 minus 1. Okay, so let's do a little dot, dot, dot here. Let's start with -6, -1, 4, 9. Okay, 4 is all the natural numbers. No, x is in the natural numbers such that -2 is greater than x and less than or equal to 7. Oh, it's all of the natural numbers between -2 and 7. Yeah, okay. I see why they wrote it like that. That makes sense. That makes sense to me. Yeah, okay. Okay, I see. Okay, so all the natural numbers between -2 and 7. 1, 2, 3, 4, 5, 6, 7. We're including 7. Beautiful. Okay, let's do 7. I'm just kind of doing a few of these. X is in R. X squared plus 5x is equal to -6. Right, all of the real numbers such that x squared. Oh, it's all of the real numbers such that x squared plus 5x is equal to -6. Hmm. Interesting, interesting. So if x squared plus 5x, oh, okay, okay, fun, that's fun. X plus 5x is plus 6 is equal to 0. Wow, this is gonna have some complex roots, I think. All right, let's do the quadratic formula. Uh, okay, x is equal to, is this it? I forgot the quadratic formula. Plus, minus the square root of, oh no, it's a negative something. Negative something all over 2a. Yeah, square root b squared minus 4ac divided by 2a. But what is the first thing? Is it negative b? It's like negative b plus or minus the square root. Damn, let's look it up. Let's look it up. All right, quadratic formula. Let's go. No. Negative b. It was negative b. Beautiful, beautiful. Okay, negative b plus or minus the square root. All right. Which means we got a is 1. Negative b is negative 5 plus minus square root of 25 minus 20. Okay, no, we don't have any imaginary roots. I thought we were going to have imaginary roots. I'll divide by 10. All right, so what does that give us for x? X is going to be let's see, square root. Okay. Oh, well, I've done this wrong. No wonder it seems weird. Because this this is not 1 times 4 times 1 times 5. This is 4 times 1 times 6. 24. There we go. There we go. Negative 4 tenths and negative 6 tenths. And which is also negative 2/5 and negative 3/5. But okay, we need all of the x in the reals. Okay, so this thought we might get the empty set. If that was the naturals, we would get the empty set, right? Got a cubic. Why also well, right, it's the same stuff. It's the same one we already solved because x0 is our last one. Okay. All right. Okay, so what is our final set? So we have a set that looks like this. -2/5. If we could do it in order, actually. Let's do it in order. Beautiful, beautiful. Okay. Next one. Let's do 15. Let's go down to the bottom. 5a plus 2b, such that a, b are in Z. Didn't we already look at this one? I thought we already looked at this one. Maybe not. Maybe it was a different example. Okay, so the main thing is, what integers can we create from two integers in Z? Okay, let's write down x. 5a plus 2b such that a, b, and z. Okay, so is x equal to z? Let's figure that out. Let's figure that out. Okay, so first, we know that everything in x is in z because 5a plus 2b is definitely an integer because you're just adding and multiplying integers. So really we need to see if, let n be in z, then can we find an a and b that create n? Right. Plus 2n minus 2n, right? Oh, no. Excuse me, minus 3n. That's what I wanted. Yeah. 5n plus 2n minus 3n. There we go. Which is then going to be 5n plus 2. What the fuck am I doing here? Okay. Let's do it like this. Plus 4n minus 4n. Right? There we go. Which is then 5n minus 4n, which is then 5n. These are in Z, so we can have all the negatives we want. Plus 2. Negative 2. N. Let's do it like that. Boom. Okay, so A and B are n and negative 2n, right? Because that will give us n. And since 5n and negative 2n are both in Z, since 5n and negative 2n are in C, then n is in X. Okay, cool. Let's finish thus x equals Z. Let's go, let's do 20. Okay, we got negative 8, negative 3, 2, 7, 12, 17. Okay, so this is clearly going to be, it's just increasing by 5 every time, and it starts at 2. It's going to be 5a plus 2 such that A is in Z. Done. Done. Let's do 27. Let's do 28. The one with pi. Screw it. Let's do 27. We gotta work the one with pi in it. Come on. Okay. That's 0. Pi over 2 pi. 3 pi over 2, 2 pi. It goes 1, 2, 3, 4, and then it's being multiplied by pi over 2. It's actually not that interesting. But then again, none of these are very interesting. Actually, what about 26? 26 seems weird. Let's just do this one really quickly. It's actually really simple. A, such that A is in Z. Done. Get out of here. 26 x is, okay, it's weird because we got fractions, 1 over 27, 1 over 9, 1/3, 1, 3, 9, 27. Oh, oh, I see. Oh, I see. Oh, how clever. Okay, so it must be, I think the integer increase is happening in the exponent, right? So this is going to be like 3 to the a. That's exactly what it is. 3 raised to the a, such that a is in z. Oh, how fun. How fun. Okay, let's move on. Section C. Find the following cardinalities. Let's try the first one. Okay. I don't know why it took me so long to process that. This is easy. This is freaking easy. You basically just need to figure out how many elements there are. And they try to trick you with all these fucking braces. This is so ridiculous. When are you ever going to see a set like this? All right, this one, I think it has 3. I'm seeing 3. Let's do 33. X is in Z, such that X is less, the absolute value of X is less than 10. Okay, okay. So that is going to be -9, -8, -7, 5, -4. I don't know why I'm putting all of these in here, but I'm already halfway, so let's just keep going. All right. This is 19, right? Probably 19. Close enough. Let's do 38 here. X is in the natural numbers such that 5x is less than or equal to 20. X is in the natural numbers such that 5x is less than 20. Okay. So it's going to be 1, 2, 2, 3, 4. And the cardinality of 1, 2, 3, 4 is just 4. Nothing to it. Nothing to it. See, guys? See, math is easy. Math is so easy, guys. All right, the Cartesian product. Given two sets A, B, multiply them. Yeah, okay, look at that definition. Definition, ordered pair. X, Y have two things, X and Y, enclosed in parentheses and separated by a comma. Wow, beautiful. Wow, look at that ordered pair of sets. Aren't you clever? Oh, an ordered pair with the real numbers and 1 point. Yeah, the Cartesian product is just the set of ordered pairs for A and B. Okay, look at that. A, B, finite, then A cross B to, okay, R cross R. Wow, the plane. Look at that. R cross N, bunch of lines. N cross N is a bunch of dots. Very cool. It is even possible for one factor of a Cartesian product to be a Cartesian product itself. Oh my gosh, you can nest these things. Look at that. Find of three or more sets by moving beyond ordered pairs. An ordered triple is a list. Cartesian product of three sets. Wow, look at all those. Mindful of parentheses, there's a slight difference between R cross N cross Z and R cross N cross Z. The first is a Cartesian product of two sets. Its elements are ordered pairs. The second is a Cartesian product of three sets. Its elements are ordered triples. If you've done programming, you will understand that greatly. It's like, why do I have an object of two numbers? Or why do I have a list of two numbers instead of just two numbers? Right. Because I'm getting back a list. All right. To the end, but yet have slightly different shades of meaning. Consider, for example, the set of all 2x3 matrices with entries from R. This is not really all that different from the set. The elements of these sets are merely certain arrangements of six real numbers. Despite their similarity, we maintain that M is not equal to R to the 6, for 2x3 matrices are not the same things as sequences of six numbers. Of course. Cartesian product can also be represented with powers. So A cross A cross A to the third. A and B are sets. Every element of A is also an element of B. Then we say A is a subset. Lovely. And we denote this as A subset B. All right. Now we're getting to the real juicy stuff. The empty set is a subset of all sets. That is, empty set is a subset of B for any set B. If the empty set is not a subset of B, then there is at least one element of the empty set that is not an element of B. But there's no elements of the empty set. Given set B. What am I looking at here? Making a subset can help us list out all the subsets of a given set B. As an example, oh, he's about to get to the power set, that's why. Yeah, that does give you all the subsets. Look at that. If a finite set has n elements, then it has 2 to the n subsets. For a slightly more complex example, consider listing the subsets of B equals 1, 2, and 1, 2, and the set containing 1, 3, 1 and 3. This B has just 3 elements. At this point, you probably don't even have to draw a tree. What about 10? I think it's going to be empty. It'll be all the natural numbers, all the subsets of the natural numbers with a cardinality of 1. We found the one with a cardinality of 0. It's just the empty set. So I think it'll just be like this. Down the line. Cool. This one, I peeped that one. I was like, oh, that's easy. That's the empty set because there's no subsets with a cardinality of 4 there. And then this one is also very easy, and I don't want to write it down. Okay. 13. Yes. Yes. F A N R U. That's easy. 15. Xy is in R squared. X minus 1 equals 0. 1 equals 0? Oh, yeah. So x squared minus x equals 0. So xy in B. Boom. Yes. All right, last one. Oh yeah, let's do it. It's gonna be, this is no, because let's just find that counterexample. 0, 1 is in B, and since 0 minus 1 equals -1, 0, 1 not in A. All right, cool. And that's as far as we got. Boom, done, easy peasy. How long was that? An hour and 19 minutes? That was not too bad. That was not too bad. Okay. All right, so last time we went through some subsets. We went through what the Cartesian product was. We went through sets, the Cartesian product and the subsets. Okay, power sets, easy. It's just a set that contains all the subsets of A. Nothing too crazy there. Look at that. The power set of this is all of that stuff. And we already saw that a set with a cardinality of n has 2 to the n subsets. So, okay, yeah, whatever. All the subsets of this. So interesting. Not that interesting. At least not right now. Okay, yeah. Let's do some subsets. Some power sets. I don't even want to do these. I feel like it's just not interesting enough. The power set, if A has a cardinality of m, then this is 2 to the 2 to the 2 to the m? 2 to the 2 to the 2 to the m. I think that's the cardinality of that. Amazing. Okay. Get on to the union, intersection, difference. Okay. The union of A and B is the set such that x is in A or x is in B. All right. Let's put these down. All right. Intersection is and, union is or, and difference is it's in one and it's not in the other. To x in A and x not in B. Look at that. The union includes all the letters. The difference includes all the letters in A that are not in B. All right. Don't think I'm going to do exercise for this one either because I just don't think there's anything we need to do there. All right, complement. This one I honestly don't quite remember. So this actually is going to be new stuff for me. I don't even remember what the complement is. Let A be a set with a universal set U. The complement of A, denoted A bar, is the set U minus A. And what is the universal set? Okay. Anything not in P should still be in N. The larger set N is called the universal set, or universe for P. Okay. So let's see. Let's do an example. Let's do one of these here. A is 4. Okay. So A is equal to 4, 3, 6, 7, 1, 9. B is equal to 5, 6, 8, 4. And U 0, 1, 2. Come on. 0, 1, 2, 3, 4, 7, 8, 9, 10. is the universal set for both. We don't often see this. Universal set, complements. I feel like this is something you don't use a ton. Probably I don't really remember it, so okay. 1A bar A is equal to everything that is not in here. So we got, let's see, 0, 2, 5, 8, and 10. Lovely, I'm sure B, yep, there we go. B is bar, B is equal to 0, 1, 2, 3, 7, 9, and 10. Crazy. Okay, look at this, look at I. That's such a ridiculous one. Let's do, I thought that there might be a bar of like the union of the two. Let's do that. Okay. Bar A U B is going to be, so what's the union? Okay, so you don't have 0 in there. You don't have 2. It's actually, I think it's equal to the intersection 2, 3, 4, 3 and 4 and 5 and 6 are in there and 7's in there and 8's in there and 9. Okay, then 10. Let's see. Bar A N and bar B. And what is that? 0, 2, 10. They are equal. I bet that is universally true. But I'm not going to prove it because I don't really care. Okay, Venn diagrams, let's go. Sometimes helpful to draw informal, schematic diagrams of them. In doing this, we often represent a set with a circle or oval, which we regard as enclosing all the elements of the set. Does this really need to be explained? We can understand. Venn diagram is just a way to showcase these set interactions, unions and intersections and complements and whatever. What is this? That was saying the expressions shows how to draw a Venn for A union B intersects C. I see. They're just using lines for A union B and then C, and any place that it is checkered, so just lines, is the intersection. It's a clever way to do it. Well, you think we're going to draw some Venn diagrams? No, we're not going to do that. Oh, this is kind of fun, though. Let's do these. These are actually kind of fun. Section 1.7 Venn diagrams. That is going to be, let's see. B intersect C, removing A. Yeah. B intersect C, and then you're taking out the part that is in A. These are a little fun. All right, what's 12? 12 is 12 is a weird one. Okay. God, what is this? Okay. It's A minus, oh God, what? Okay, how are we gonna do this? How are we gonna, because this spot in the bottom is, how do you even describe that spot? That would be A subtract B union Oh God, that's such a weird spot. Okay, okay, okay. How? Let's do it like this. Here, here, here. This is a good way to represent it. A minus B, right? That gives us this moon here. A minus B. Okay, and then we'll union that with C intersect B. There's definitely always going to be like a lot of different ways to write these, which makes them kind of fun. But what's like the simplest way to do it? I think that's the simplest way to do it. Okay. This one's fun. This one's fun. Yeah, this is going to be A, U, B, U, U, C, minus A intersect B intersect C. It's anything that isn't in all three of them. Yeah, it's all of them, every element that isn't in all three sets. That's a fun one. I like these. I like these problems. All right, 14. Yeah, do it like this. A minus B union C. Union. Union is basically your addition, right? Union is addition. Difference is subtraction. Intersection is, I don't know. It's kind of a bad analogy, actually, now that I think about it. A intersect B intersect C. That's pretty good. Okay. Index set when math involves lots of sets, it is often convenient to keep track of them by using subscripts. Wow. What? Does that really require a whole section? It's funny, but I mean, it's worth saying, you never want to assume people know something and then they don't know something. Yeah, the big union and the big intersection. I actually forgot about this. That's pretty good. We'll just write that down. 0.8. Okay. You can index sets like you can numbers, and you can index a sequence of unions and intersections like you can sums and, let's just say sums. I don't know. I needed a second thing. Can also write down an infinite sequence of unions and intersections this way. Lovely. Now we're getting to a point where it's like the notepad is restricting. We definitely will need to use LaTeX eventually, even for just like notes and problems and stuff, because it's just not feasible to do it on Notepad here. This example, all sets A sub alpha are all subsets of the plane R squared. Each alpha belongs to the index set I equals 0, 2. Each alpha belongs to the index set, which is the set of all real numbers between two. Note that these sets are not indexed with just integers. For example, as root 2 is in I, there is a set. Okay, and what is each of these? The set A sub alpha is alpha to 2 Cartesian product with 0 to alpha. Oh, I see. Oh, I see. Okay. So the boxes are all contained within this triangle, but they have a length and height basically determined by alpha. The infinite union. Yep. The infinite union is just going to be this triangle. Lovely. The intersection is going to be 1 point. Yeah. 0.02 on the lower. Yep. 2, 0 is included everywhere, so the intersection is just 2, 0. Okay, lovely, lovely. You are doing some 3D nonsense here. Do I skip this? I think we're just gonna. I mean, it's not bad. It's not bad, but actually, these would be kind of interesting. Now that I'm looking at them, I'm like, this is kind of interesting. I don't care about the finite ones; those are boring. Let's go down here. 4a. What's 4a? For each n in the natural numbers, let a sub n. Let's write this down. For each n in n, let a sub n negative 2n 0 2n. Okay. Big U sub I in n. I don't know how to do this notation. It doesn't really matter. It can be ugly because, yeah, whatever. All right. U sub I in n, a sub I is equal to the union of all of these. It's a series of or a series of sets. It's a union of all the sets such that negative 2n, 0, 2n. I mean, it has to be n, right? It has to be. It has to be because, oh, not n. No, it has to be z. Excuse me. It has to be z. Z, 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 z. You can make. Oh, no, no, no. It's the even integers. It's even integers. All even integers. The intersection is just 0. Easy peasy. The union of I comma I plus 1, I to I plus 1 for all I and n, that will be, brackets are inclusions. Okay, let's do 5a. This is just going to be, we're starting at 1, comma, inf. I'm too lazy to write this out again. Intersection of all of these, empty set. All right, let's keep going. 11 and 12 might be kind of interesting things to write out, like actual real problems. 11 plus 12. That'd be kind of fun, like, to prove. Well, it's 12 is not proof. None of these, neither of them are proofs. So we haven't learned about proofs yet, technically, but we can do them. But I think this one is always true. That seems right to me because if you are in every single one of these, you're in at least one of them, right? That's easy. If they're equal, what do you think can be said about the relationships between the sets A sub alpha? I think it has to be a bunch of subsets of each other. No, no, no. They all have to be the same. I think they all have to be the same. I think they're all the same set. Because if you're in all of them, if you're in one of them, you're in all of them, right? So they're the same sets. Yeah, okay, okay. Definitely 12 in the same sets. If J is not equal, if the empty set in J is a subset of I, does it follow that for all alpha in J? Yeah, I would think so. I think that's true. Does it follow that yeah, because the set, for any one of these that are in J, for let's say a beta in J, the set alpha sub beta, A sub beta is in here somewhere. And since beta is also going to be an I, A sub beta is going to be in here too. So you can do some element analysis there. And I think this is also true because you have to be in every single one of these sets, which means, I mean, I think that's true. No, no way. No, no, no. There's no way. Oh, wait, hold on. No, this is smaller. So actually, this is not true. No, no, excuse me. This is not true. Because this is the intersection. Actually, this one I'd have to think about. Now I'm not so sure. I'm not going to really think about it too much. But it could be. Actually, no, I don't think this is true at all. Let me actually think about this. Okay, so if alpha, let's take a beta in J. There's an alpha sub beta here. Yeah, this is definitely not true because just take something where I contains let's denote the empty set as A sub 1, right? And let's make I a set that contains 1, and then J is a subset that doesn't contain 1, right? So the empty set would be in this intersection, making this an empty set. This wouldn't necessarily be empty. Yeah, you can come up with a counterexample. Yeah. So this is not true. But I think this one is probably true. Yeah, that seems like the right direction for that subset to go. Because if you're in all of the sets here for all of the elements of I, then you're at least in some. This is less sets. The intersection with the J is less sets that are being intersected. So since you're in all of these sets, you have to be in all of these sets because of the subset direction here, right? Cool. Sets we tend to be most interested in often have special properties and structures. For example, the sets Z, Q, and R are familiar number systems. Given such a set, any two of its elements can be added or multiplied, etc., together to produce another element in the set. These operations obey the familiar commutative, associative, and distributive properties that we all have dealt with for years. Such properties lead to the standard algebraic techniques for solving problems. Even though we are concerned with the idea of proof, we will not find it necessary to define, prove, or verify such properties and techniques. Okay. Ordering the elements. Sure. Okay. Number order tells us is that any non-empty subset of n has a smallest element, right? Cool. This fact is sometimes called the well-ordering principle. Amazing. Remember this term, but do be aware that we will use this simple, intuitive idea often in proofs, usually without a second thought. Yep, you do. You do. The well-ordering principle seems innocent enough, but it actually says something very fundamental and special about the positive integers n. In fact, the corresponding statement for the positive real numbers is false. That is true, but it does have a supremum and an infimum, and that's just as important for the real numbers. The subset A equal to 1 over n. Yeah. So use the familiar fact that any integer a can be divided by a non-zero integer b, resulting in a quotient and remainder r. Not sure how those follow, but I'm willing to just accept it without a second thought. Given integers a and b with b greater than 0, there exist unique integers q and r for which a equals qb plus r, 0 less than or equal to r less than b. Q and r for which a is equal to qb plus r. Okay, let's skip this. It's not important. Skip it. Let's go to Russell's paradox. Boom, Russell's paradox, and then we're on to chapter 2, baby. Okay, let's see it. This section contains some background information that may be interesting, but it's not used in the remainder of the book. Let's do it. Let's look at it. The philosopher and mathematician Bertrand Russell did groundbreaking work on the theory of sets and the foundations of mathematics. He was probably among the first to understand how the misuse of sets can lead to bizarre and paradoxical situations. He is famous for an idea that has come to be known as Russell's paradox. Russell's paradox involves the following set of sets. A is such that x is a set and x is not an x. In words, A is the set of all sets that do not include themselves as elements. Rut-row, the barbershop paradox. Most sets we can think of are in A. The set Z of integers is not an integer, and therefore Z is in A. Also, the empty set is in A, because the empty set is not in the empty set. Is there a set that is not in A? Consider B equaling... I don't need... Okay. Think of B as a box containing a box containing a box containing a box, and so on forever. Set of identical Russian dolls nesting one inside the other endlessly. B is that it has just one element, namely B itself. Oh my gosh. Thus B is in B. As B does not satisfy, B is not in B. It says B is not in A. Okay. Russell's paradox arises from the question, is A an element of A? Uh-oh. For a set X, equation 1.1 says X is in A, means the same thing as X not in X. So for X equaling A, the previous line says A is in A means the same thing as A is not in an A. Oh man, that's no good. Initially, Russell's paradox sparked a crisis among mathematicians. How could a mathematical statement be both true and false? No, this seems to be in opposition to the very essence of mathematics. The paradox insisted a very careful examination of set theory, and an evaluation of what can and cannot be regarded as a set. Eventually, mathematicians settled upon a collection of axioms for set theory, the so-called Zermelo-Fraenkel axioms. One of these axioms is the set of axioms that I know exist. I can't name any of them except for the one that is one of those axioms is the well-ordering principle of the previous section. What? That's an axiom? Oh my gosh, I actually didn't even know that. That's kind of cool. I would not have guessed. I would guess that you could define n and then prove that. Interesting. Another, the axiom of foundation, states that no non-empty set X is allowed to have the property X intersect little x is not equal to the empty set. Wait, hold on. States that no non-empty set X is allowed to have the property X intersect an element of itself. X intersecting an element. Okay, so X has to be able to intersect one of its elements to be the empty set. That's what you're saying. For all sets X, they have to contain an element such that when they intersect that element, it's the empty set. Okay. So just define sets as B. Oh, okay. Okay. I see. I see. You can't have this self-referential part of the set. Like the sets cannot reference themselves. That's what they're saying. You can't have the set contain itself. That's what that is saying. That is what that is saying, because when you intersect, you're getting the empty set. Wait, no, that's not. Wait, hold on. That's not right, because well, I think about this is confusing me because when the one element that it has, it intersects with itself and it's empty. Isn't that the requirement? X is allowed to have the property. Oh, wait. Yeah, okay. B intersect B. Something in a set intersecting itself is the setback. I see. For all of the elements of this set here, this proposed set, when B intersect B is equal to B, which is not an empty set, which means this property, yeah, is not empty, right? The intersection is not empty for all of the elements of B. Didn't happily ignore problems do not tend to come up in everyday mathematics. You have to go out of your way to construct them still. Okay. Additional reading on sets for a lively account of Bertrand Russell's life and work, including his paradox. See the graphic novel, Logic Comics. I honestly should get that, because I do actually kind of want to get that book. I had that a long time ago, or I had it a long time ago, and then I think I've lost it. I've since lost it. All right, chapter 2 will be next time.